class. Today's tutorial will be on how to interpret an energy cycle diagram. Here's an example of an energy cycle diagram. An energy cycle diagram is reminding us that when we calculate the enthalpy of reaction, it doesn't matter which pathway we take to get from the initial reactants to the final products. The enthalpy value will be the same. So in this particular energy cycle diagram, there are two pathways by which I can produce my final products B. I can take the pathway from A to C to B, which means that my enthalpy of reaction 1 will be equal to the enthalpy of reaction 2 plus the enthalpy of reaction 3. So if you're looking at an energy cycle diagram, there's always two ways around the cycle. And so this pathway I could take to make B, or I can take this longer pathway to make B. But either way, the two ways I can get around the energy cycle are always equal to each other. Now, the other way I can do is I can go this one way, which is H1, and so this pathway will be equal to the alternate pathway, the pathway that goes from D to E and from E finally to B. And so the enthalpy would be H1 would be equal to H4 plus H5 plus H6. So in any energy cycle diagram, there are two possible pathways, and those pathways' enthalpies are equal to each other. So how do I use an energy cycle diagram to calculate the enthalpy of a reaction of interest? Well, first I'm going to find those two roots around the energy cycle diagram, and I'm going to make them equal to each other. And the trick for finding the two roots is finding out in which direction the arrows are mostly pointing, and we'll practice that in a second. Then I'm going to add up the enthalpies of one side and the enthalpies of the other, and they will be equal to each other. And I'm going to solve for my missing enthalpy, which will always be the delta H reaction of whichever reaction I'm interested in. Now, just like with the other ways that we calculate enthalpy, we need to multiply the enthalpy if there is a coefficient in the balanced chemical equation. So how does this look? Here's our first energy cycle diagram, and as you can see, the blue arrows show us the two different pathways around the energy cycle. So if I look at where the arrows are pointing, they're all pointing here towards my product. And so I can see there's two pathways to get there. I can get there, so here's my starting point. And the starting point is boxed. Many teachers like to have their students box the starting point so you can see how you're going around the cycle. So I have this pathway. I could call this, let's see, we call this A, we call this B, and we call this C. So I have my pathway from C to B, and then I have my pathway from C to A, and finally to B. So I can say that the enthalpy of my pathways from C to A, which are my two enthalpies right here, plus the enthalpy of my reaction that I don't know, is going to be equal to the other pathway, which is the C to B pathway, which is negative 109 kilojoules per mole. Now I need to solve for my unknown, which is delta H, so I'm going to isolate it, and I find out that when I isolate it by subtracting 52.2 kilojoules from both sides and adding 92.3 kilojoules to both sides, I find out that my enthalpy of my unknown enthalpy is going to be negative 68.9 kilojoules. So I would say with these problems, the most difficult part is sort of determining what are your two pathways around the energy cycle diagram. Let's look at one more sample. Ugh, I hate it when it does this. All right, so here's a second cycle, and once again you can see the two pathways that have been drawn around the energy cycle diagram in this way, and then again we've boxed that place that all the arrows are pointing to. So we know that our two pathways is this pathway, the delta H and the negative 3267 pathway, and the second pathway is the 394 and the 286 pathway. Now notice we have coefficients in this particular example. So I'm going to multiply my enthalpies by those coefficients. And remember, if I have, these are moles, and these are kilojoules per mole, so my moles will cancel, so my enthalpy is always going to just be in kilojoules, unless of course it is a molar enthalpy. And then once again, I know that this pathway, the delta H 326 pathway right here, is going to be equal to the other pathway. Since they're just alternate ways of getting to these, these compounds. Even though this is the reaction of interest, my alternate pathways are pointing in this direction. And so I'm going to multiply my two enthalpies for the other pathway by their coefficients. And I discovered that the delta H for my reaction of interest is a positive 45 kilojoules. So these enthalpy cycle diagrams just remind us of the first law of thermodynamics, which basically tells us it doesn't matter which pathway I follow from the reactants to the products. All pathways will have the same enthalpy.